arrangement, which is very much necessary for this subject understanding, and then we'll go for stereographic projection. Okay, so first we have to learn what is atomic arrangement with the different materials. There is a crystalline material and non-crystalline or amorphous material. When the atomic arrangement are periodic, means there will be a pattern every certain distance. You will see the repetition of atomic configuration or arrangement. Then you can tell those are the crystalline material. And metallic system are basically crystalline. And if there is a different kind of small oriented portions are there, then they are named as a polycrystals. Means many number of small crystals are make a total bulk of metallic system. So then you can tell the polycrystal means gain boundary. Those things we will learn slowly later. So first we are going to concentrate about the two-dimensional lattice. First, if you look at, there is a in figure number 1a. This is a two-dimensional lattice indicating several possible sets of primitive basis vector. Basis vectors, if you want to understand what is basis vector, it is nothing but a kind of vector which are minimum distance between two lattice points with a particular arrangement, and after that there will be a repetition. So each basis vector in particular direction, there will be a repetition unit, you can tell. So now if you want to know a unit cell, then what is the unit cell should be? What a unit cell does mean? So if you want to create a unit cell, so then the following things what I am going to tell, those things you should remember, that a unit cell should contain very few number of atoms, means fewest number of atoms, means this should be the minimum number of atoms for that particular atomic arrangement a unit cell should contain. And unit cell should have angles closest to 90 degree, if not 90 degree. If you get 90 degree, if it is a cubic system and tetragonal system, then it is a very good. If it is not, then you have to go for closest to the 90 degrees. And the unit cell should process or should have the property of containing most symmetry of that particular atomic arrangement. Means whatever the symmetry element are available, they exhibits the most symmetry element. So these actually create a unit cell. So these are things you have already learned from the previous subject in different previous semester, but we have to touch up. And now if you look at in the picture figure 1b, there you can see the translation along y-axis, then translation along x-axis, and then translation along z-axis make a three-dimensional arrangement of a bulk system with having different unit cell. So crystalline solid can be constructed such a way. So you can say that if we can take a unit cell, then we will translate those unit cell at three different direction x, y, z, and then we can get a crystalline solid block. Now I will touch up with the different crystal system and their symmetry elements. So figure number 1a in this slide, if you look at, a line is bisected with a plane normal to it. So here just one section is there, then the line is actually, all the lines are bisected is of the normal. So till date we know that a plane is recognized by its normal direction. So how it will recognize the plane? How it will recognize? It will recognize by its normal direction normal. So what will happen if you construct all the planes with that normal to that directions? given in the figure number A, you will get figure number B, that is weaknesses cell. We have a concept that it is a kind of cell where you can see that all planes are normals are bisecting each other in the 90-degree angle. So bisected each other. So now there are different kind of two-dimensional geometry you can say can be present as square, hexagonal, and there should be a relationship. So what are the key aspects one should remember when one should understand about the crystal system? Aspects number one, the lattice point. What is lattice point? The lattice point is the point where he should have similar environment around that point. So that should be very one should remember. Then I already told about the unit cell. Unit cell should process the most number of symmetry. Now another thing one should remember, then when you are looking at such kind of things, then the one crystal or unit cell should have all kind of periodic arrangement. If you set those unit cell and just stack them, and you can construct a crystalline solid. Already we know that from the just 1 minute ago discussion. Now what unit cell should process? Most symmetry, and so there should be a certain construction features. What are those? Now that should be a close the angular relationship should be there. There should be a basis vector that certain vectors that in the three direction a1, a2, a3, and another thing should be that should translate and get a proper construction of a particular crystalline solid. So if you look at the different way you can see in the here one figures 1c, this is as a general three-dimensional unit cell, and 5 types of two-dimensional Bravais lattice are given in the right hand side of the slide. So it may be square. What should be the features of the square? A1 equal to A2, and the angle between two basis vectors should be 90 degrees. Same way you can understand hexagonal, then rectangle, then centered rectangular, then oblique. So these are the Bravais 5 types of Bravais lattice. We are just brushing up. So we should keep in mind when we are going along with this subject. Understand the subject. Now we also have a little bit. We should have a little bit of understanding of the symmetry element associated with the crystalline metallic system or crystalline material. So what are those? One is translational. That is, if you see every certain distance, things are repeating. So you can tell that is a translational symmetry, because after certain distance, it is just repeating. And if you have a concept of lattice vector, then you can tell that this is the lattice parameter, after which the atomic arrangement will be going to repeat it. So it is a translational kind of symmetry. Then rotation after certain angle, if the things are like that, that it is repeating, you are saying same thing, then you are going to tell that that is rotational symmetry. And then if you have a mirror image of some atom with respect to another atom or certain particles, this is a mirror symmetry. And then screw diode symmetry is just you just move like a screw, and then your diode means 180 degree. Diode means 180 degree rotation. So this is screw diode, and then another kind of symmetry is a glide symmetry. This mirror, then is shifting. So mirror image plus certain distance or certain periodic distance translation. So these are the basic concept of symmetry which is required for this subject understanding. Now we are going to understand what are the different symmetry element associated with different crystal system. So if you look at cubic crystal system, so threefold rotation axis is there. So if you take the diagram of the cubic, and we know all of you understand what is the Miller indices of a particular plane, what is the diagonal of a particular cubic system. So if it is a 1-1-1 direction or diagonal of that things, and then you can see that there will be, if you move that, you will have a threefold rotation. Threefold rotation means whatever fold you are going to take, you just divide that by 360 degree by that number. So there will be a 120-degree rotation. After that, things will be same. Then four such kind of possibility should be there. Means four such kind of diagonal system and such kind of direction should be there, where the rotation axis should be there in that particular system. Same way tetragonal, there is a fourfold rotation axis is there, and then orthorhombic, three perpendicular twofold rotation will be there. Then rhombohedral, threefold rotation are there. Then hexagonal, one sixfold rotation are there. Then monoclinic, one twofold rotation is there, and triclinic, there is no symmetry element are going to exist. So we are generally concentrate on the cubic system, and sometimes hexagonal closed packed system, the magnesium kind of for the understanding of the deformation behavior of magnesium. But mainly we are going to focus on the cubic system, body center cubic, face center cubic kind of. Body center cubic example is body center cubic example is iron, and face center cubic example is aluminium or copper. So that way we can understand and those things, and then ACP magnesium little bit. Now we are going to understand the different lattice planes, how it is important because we have to understand where the deformation we are going to occur, how the deformation different plane are associated with this closed packed plane, where the different defects can occur, and how they play the plasticity of the particular material. So before we start that, I just want to tell one information that when you are going to represent direction, that HKL calls, then it should be in the third bracket. HKL in the third bracket, it actually shows the direction. Families of direction, it can be right like that. Open bracket, the triangle shape bracket with a HKL direction. And then planes, HKL plane, and that should be in the first bracket, and families of the plane in the second bracket. All those things already we have gone through, but we should be very much careful about these things. In the chat box, I have given the nomenclature of such kind of directions, families of directions, and the planes and families of the planes. Now here you can see the different kind of planes are with their Miller indices are given, so that one can understand and how it is going to construct. Everybody knows but how to calculate the meter with respect to intercept. So these are the general lattice plane one should understand, so that when we are going to understand that what will be the angle between tensile axis with that particular plane, then you can easily calculate very easily, and so that so everybody should brush up this part of the section, that atomic structure, Miller indices of lengths, and also the different planes, at least for the cubic system. Now we'll start a mostly new thing for you, that is idea of stereographic projection, which is very much essential for this subject to understand even certain characterization technique of materials engineering or science, whatever you tell. So if you look at that picture, then here we are going to understand why stereographic projection are very special and what are the why that particular way one should construct. So if you want to construct a 3D projection, 3D to a 2D surface, represent a 2D surface for a 3D material or 3D system. How to do that? So that the two way we can do. Directly we can do in the first figure, in the just left hand side figure, if you look at, you can directly just project on a particular surface parallel to the equator or the middle of equator plane, and directly you can. And then what will happen? The circle will become a ellipse. So you will lose the actual right angular truth. The actual angular truth you are going to lose. So that should not be correct way to represent stereographically particular crystalline system. So then we are going to understand the second way, which is the perfect way how to retain the angular truth. The second figure you can see, we are having our south pole in just the bottom point is there, and from there we try to connect each point we are going to project in the equatorial plane, and then the equatorial plane are going to cut there. And if you just get those projections such a way, then the angular truth are going to be retained. Okay, so south pole, equilateral plane, and north pole. If you look at the third figure, then this is the AB circle is there. And if you look at that AB circle in the surface of the sphere, also the projection in the equatorial plane is also a dot b dot. This is the surface, and how the projection has been done. Now all the point in the perimeter of the small circle, that is AB, are connected through the equilateral plane to south pole, and then all the point which are the projection of in this method on the equilateral plane are going to connect to draw the A dot B dot, and in this way you can actually keep the angular truth without any kind of deviation. So you can protect angular truth in the process, so that actually really helpful for the purpose of stereographic projection. That's why this kind of method has been taken. Now we are going to understand the little bit of critical part of how you are going to understand stage by stage the idea of stereographic projection, how to develop the concept, how stereographic projection are going to apply for such kind of relationship. So if you start with the stage one, then look at the pictures. The structural line or plane is projected onto a sphere. So suppose you can start by projecting a structural line. Figure A actually shows such a line as it observed in the actual, you can tell in the surface of the sphere. Alongside, if we can imagine a hollow sphere, and line is now shifted from the outcrop and without rotating it placed at center of the sphere. That is, if you look at the picture, see now the length of the lines increased downward until the line meets the sphere surface. So the point where the line and sphere meet, it called the spherical projection of the line. You can tell that. And this point is always located in the lower half of the sphere, and it is the exact position depends on the orientation of the line. So now we are, it is a little bit of tricky. So please understand. Again, I am repeating that. Suppose if you look at figure C, the length of the line, it actually going to increase when you are going downwards until that particular or that very line and the sphere meet is called the is that the point at which the line and sphere are going to meet is, you can name them the spherical projection of the line. Now this point is always located in the lower half of the sphere. If you look at the picture, now next part of that stage 1, we are going to understand what is the plane. Suppose if you look at the figure number B, hope you are able to see figure number B. So if you look at figure number B, then you can see that a plane actually is going to project it in the same way what we have done few seconds ago for line. It is translated to the sphere center and extended down until it touches the surface of the lower hemisphere. The line of the contact is now a circle. Okay, so a circle on the sphere with the same radius as the sphere itself. So such circles on a sphere which are produced by the intersection of a plane which passes through its center, you can tell that this is a great circle or greater circle, great circle. Okay, you can correlate these things with the concept with the earth. Thinking of the earth, you can tell that it is an approximate sphere, or you can also correlate with the normal sphere, and the lines of the longitude are great circle, so it is a equator. However, if you look at the figure number 6, figure number E, the figure number E, where you can see that the lines of longitude are great circles, so you can tell that it is in the equator. Now, but there are other circles on that sphere, such as polar circles. So you can also understand that different great circle you can do based on different lines and planes. So now you have to think one thing. Let me so now we are going to talk about next stage, that is stage 2. In stage 2, points and the great circles from the lower hemisphere are going to project on a flat piece of paper. So then we first take a plane on which the projected things are going to say everything the plane of projection. We take horizontal line as our plane of the projection, and then what again? Please understand. Then we are going to place it so that this is passes through the center of the sphere. So now what is happening? If you see the final result, the final results of the projection is to produce a representation of a flat piece of a paper on a 3-dimensional orientation, and that actually you can tell the stereogram. Now next stage is the understanding the properties of the stereographic projection. Okay, we understand how to draw the stereogram, but what is the uses? What are the different properties of that stereogram? Now we have to understand that. So of course, we can tell that there is a variety of different projection of the sphere on the particular plane that could be used to represent the angular relationship. Already I told that angular relationship to the projected things and actual thing presented in the surface of the sphere should maintain the proper angular truth. Now, next step is that, of course, we should understand that if different projection of the sphere on a particular plane, that could be used to represent the angular relation between the poles of the faces of the system. So things looks very simple, but however, what makes the stereographic projection preeminently suitable for the purpose is the fact, if you look at that it projects any circle on a sphere into a circle on the projections. So this is one important understanding. Okay. So if you look at the figure A, then you can understand that figure A or figure B in the slide, that figure actually shows the meridian of the sphere projects to a diameter of the primitive, and that is the case when the projection is the circle of infinite radius. And if you have a circle of latitude on the northern hemisphere projection, then to a circle concentric with the primitive and inside it, you can understand. So if the circle of the latitude were in the southern hemisphere, then what will happen? It would project to a concentric circle outside the primitive. So in this way, you can also see the different construction features of the stereogram. Now, I have written in the slide two important features, and those things are also shown in the one is meridian on the sphere projection into a diameter of the primitive, and the circle of latitude projection into the circle concentric with the primitive. These two things are important features or properties of a stereographic projection. Hope all of you understand that. Now we will continue the properties part and we will understand much more detail about the properties of the stereographic projection. So if you look at the equator part and meridian part, then you have to pay much more attention, because the equator and the meridian are special kinds of gate circle on the sphere. So a gate circle in a general position, if you look at the picture, it is shown. And from that, you can clearly understand that its stereographic projection is a circle of radius greater than that of the primitive. So what will happen? It intersects the latter in 2 points at opposite ends of the diameter of the primitive. The half of the great circle, which is in the northern hemisphere, projects to the arc that is within the primitive, and the half in the southern hemisphere projects to the rest of the circle outside the primitive. Please very careful and attentive when, and you can do these things by yourself, just listening my word and try to construct that, and then you can understand much better. Your own practice is required to understand this process. So for some purpose, if you are going, it is very much necessary in order to consider the whole circle. But other than that, what will happen is more convenient to project the half circle in the southern hemisphere to the north pole. So the clumsiness of the projection, or you can tell the crowding of that projection, will not be there. You can see things are very clearly to confine the position within the primitive also. When this is done, the complete representation of the great circle actually consists of two arcs of large radius systematically. Again, I am repeating, two arcs of large radius symmetrically related across a diameter of the primitive. If you want to see these things, you have to go for next slide. So there you can see the broken line shows the portion of the projection of the great circle, and that lies in the outside of the primitive. So that actually restrict us to keeping all hemisphere in a particular plane. So it is better to get half of the hemisphere and project that. That will actually going to help you. Now here stereographic projection very this part you can tell that the step by step how the particular cubic system projection can be done or stereographic projection can be done. So I'll just read it out and you can understand slowly. So if angular relationship between the faces of crystal plays an important role in determining the internal arrangement of atoms in the ordered fashion and the internal symmetry even in a disordered crystal, which displays crystal faces. What it actually is telling you? It is telling you that the different faces of crystals and their inter-orientation relationship and internal arrangement of the atom also can be determined based on the different faces of crystal, different planes present in the crystal, their internal orientational relationship. That is the basic and fundamental things which is going to play an important role to construct stereographic projection and actually eventually it will represent the particular crystalline system. So external symmetry of a crystal largely depends upon its internal symmetry, and such kind of dependency of the symmetry or angular relationship can be easily witnessed and understood with the usage of method crystallographic angle projection called stereographic projection. That is actually stereographic projection, the essence of that stereographic projection. Now, what are the steps you are going to follow? Already I have discussed the background of construction of stereographic projection and certain properties of the stereographic projection. Now, I am going to discuss the different steps you are actually going to do when you are constructing a stereographic projection or you are drawing or you are obtaining a stereographic projection. What are those? Imagine that a crystal is inside a sphere. You have to see that, and if you look at the picture, figure number 1, there in 100 poles of the cubic crystal, how it is placed, you can imagine same way. And draw a normal to the plane. You have to draw a normal to the plane, and the point where the normal intersects the in-sky sphere is known as the pole of the plane. If you look at the picture number 1, you are going to understand easily. And make a greater circle out of the projection of the plane, which passes through the origin of the crystal and onto the surface of the sphere. So this slide actually, whatever discussion I have done regarding the idea and properties of the stereographic projection are just summarized with the perspective of construction of stereographic projection. Then you are going to create a smaller circle out of the projection of the plane, and that does not pass through. Now measure the angle between two planes which are normal on the surface of the sphere to find the angle between these two considered plane or planes of your interest, and make this measurement along the greater cycle as it is shown MLK in the figure 2. Now other steps. As measuring of the spherical surface is tricky and is really tough, so one should be very careful and needs to project everything from the sphere surface onto a particular plane and consider the diameter of the sphere. Put a plane perpendicular to the diameter and in contact with one end, project from another end of the diameter through entity to be projected on that particular plane. As we create aforementioned projection, points in the hemisphere near B will end up outside of the sphere. I already told that that's why one hemisphere one should consider. On the contrary, points on the hemisphere including A will end up inside. If you look at the picture number, figure number 3, and to tackle this complicacy, change the projection point to other end and diameter and mark them points with a different symbol, maybe open or filled hole. So taking same pole and try to project two hemisphere is not possible because one hemisphere will be inscribed in the projected circle, another is outside of the primitive circle. Already, why is it so? We understand from the previous discussion. So now we understand that we have to find out certain ways to tackle that problem. It's very simple. You just change two pole and that respective Q2 both will be in the inscribed, and you have to check and identify these two things differently, then you have to go for different symbolization. That may be open or filled circle or points to distinguish among them. Okay, so that's the basic steps or the fundamental steps for drawing stereographic projection. Now, here an example that stereographic projection of a particular faces of a particular isometric crystal, that you can see that at different these things you can slowly understand. If you go to certain books, you can also refer our book, that also in first chapter. But I am telling a simple way. If you look at the center, which is the, you can see that z axis means 0, 0, 1, and then right hand, that east one is 0, 1, 0. It is a y axis direction. And then if you go for lower side, that is 1, 0, 0, this is x direction, and this just opposite to that x, the upper point, it is the direction 1 bar 0, 0, means -1. So this is just that, then -1, 0, 0 and 0, 1, 0. In between, if you want to see what is the direction that 45-degree angle orientation relationship, then it will be 1 bar 1, 0. So there's a good relationship. If you add any point in the presence in the circle, the perimeter of the circle, and get the that orientational direction in between them, that you can do within. If you look at 0, 1, 0 and 1 bar 0, 0, then you are going to get 0, 1 bar 0 and 1 bar 0, 0. Then if you add them, then 1, 1 bar 0, and then you can say that 1 bar 1 0 is a 45-degree, has 45-degree angular relationship with two plane having normal 0, 1 bar 0 and 1 bar 0, 0. That this kind of representation can be easily understood. And if you want to calculate angle between two planes, then you have to find out the angle between two greater surface, which is schematically and diagrammatically given here. So if you look at the picture, there is a two plane A and plane B, and we want to find the angle between these two planes based on the different greater circle. So then we have to find out the angle orientation relationship with greater circle. So what is the purpose of this slide or this discussion is determining the dihedral angle between a pair of planes. Here it is marked as plane A and plane B stereographically. So how to do that? You can use the method which are going to take the base depending upon the great circles. So what you have to do, you have to plot. If you look at the picture, you have to plot both planes as a great circles, and then you have to label A and B as labeled in the picture. Then line of the intersection of capital L of these planes is given directly by the point of intersection of the great circle. And then what you have to do, you have to find out the plane C, another plane which is perpendicular to the capital L and the line of the intersection, that is the line of the intersection. And then what you have to do, you have to draw on the stereogram. Plane C is the plane whose poles are going to plot at L, that is the line of intersection. Then the dihedral angle alpha can be measured in the plane C between the traces, that is line of intersection of C of planes A and B. Fine. So in this way, you can measure the diagonal angle between pair of planes stereographically. Okay, so you should remember, in order to do that, there are two angles that could be measured at this stage. But these are can be labeled alpha and alpha naught. But the acute and obtuse diagonal angles respectively you can measure between pair of planes, and these two angles, if you add up, they are going to get the value 180 degree. Now, if you also want to do the angle between A and B, another methods are available. That is a method using poles of the planes. So this kind of alternative method actually makes use of the fact that the diagonal between a pair of planes is equal to the angle between the normal to those planes. Already in the initial part of the discussion, I told that plane normals are the identification or representation of particular planes. So if we can use these features, then we can calculate or determine or evaluate the dihedral angle between pair of planes stereographically using poles of the planes. So what you have to do? You have to plot planes A and B as a poles. If you look at the last figure F, and measure the angle between the poles using the same method as already we have discussed, measuring the angle between two lines. And the angles are measured along the gate circle. One should remember, the measurement of angles always should be done along the gate circle containing that two poles or those two poles. So these angles alpha and alpha are the acute and obtuse angle, and you can add them, you are going to get 180 degree angles. So locating a particular plane corresponding to the pole. So already I told that if you wanted to get the interplane angular calculation, then how to locate? The normal to a plane is represented by a pole. So thus, if clearly you can say that means the angle between the pole and any line on the corresponding plane is 90 degree, and this may be constructed by placing the projection on a warp net. We'll understand how warp net and all those things later, and also we should know that thing regarding the warp net in the previous discussion in the last year class, but I will touch it up again next class. So in this way, but without warp net also you can do the way constructed here. If you look at figure 2 and 3, determination of intersecting point, what I told few minutes ago, and you can either trace the respective planes or represent the point where the two planes are finally meeting, and you can locate the whole consisting of both A and B plane. This is a very standard projection of cubic crystal, and here you can calculate the angle between two planes. This is their equation is based on the Miller indices, and you can say that if no two plane Miller indices, directly you can calculate their angular relationship based on this equation. This is a direct, but you have to understand how these things are constructed. For that purpose, I have discussed today class all the background for that. And then you can use this equation to satisfy certain condition to understand what will be the orthogonality between the plane. So for the plane to be perpendicular to each other, what we have to do? Now, cos theta or cos phi should be 0. How to get that? Then H1, H2, K1, K2, H1, H2 plus K1, K2 plus L1, L2 equals to 0. So in this way, you can get certain orthogonality or parallel plane conditions from this equation. And high indices plane, how to locate? That also can be done based on after locating the low indices plane. Then you are slowly construct their normal to the plane, and then you can understand the concept of zone axis, because the concept of zone and zone axis can be implemented. We know what is zone axis. to locate the poles of a high indices plane, because then only you can find out certain things, because zone axis is the axis where the certain planes are, all the planes are lie on that and parallel to that. So let the pole of different plane you can create, and with a different zone axis that can be constructed here also little bit of. And since this today lecture is mostly you can tell that prerequisite for this subject, and all the things you should already you have learned other than the stereographic position part from previous classes or previous semester. So I want that this home task should be carefully written. All these things are, and you keep with your class note also. And these two are reference book for this lecture or this section. Thank you so much for listening to the class.